So let's read this paper on model hierarchies that I mentioned last time. As usual, I'm being fairly brief. It's a nice paper. You can go and read it if this topic is of interest to you and you want further details. This is a perspective on climate model hierarchies. I showed the DOI here. Don't have the author list, but the bunch of young smart people. To understand this, climate modelers employ a hierarchy of climate models spanning a wide spectrum of complexity and comprehensiveness. This essay, inspired by the World Climate Research Programme's recent Model Hierarchies workshop, attempts to survey and synthesize some of the current thinking on climate model hierarchies, especially as presented at the workshop. We give a few formal descriptions of the hierarchy and survey the various ways it is used to generate, test, and confirm hypotheses. We also discuss some of the pitfalls of contemporary climate modeling and how the Elegance advocated for by Held, the paper we just looked at, has and has not been used to address them. We conclude with a survey of current activity in hierarchical modeling and offer suggestions for its continued fruitful development. So the idea is that we do need model hierarchies to understand processes and worry about the principles that Isaac advocates in terms of making sure that these elegant models meet the more elaboration models so that the bigger models can be improved. Okay, so this paper is nice because it starts with quotation on each section, which I will read. This is Borges on exactitude in science. So nice philosophical statements. In that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In time, those unconscionable maps no longer satisfied, and the cartographers' guilds struck a map of the empire whose size was that of the empire and which coincided point for point with it. Following generations who were not so fond of the study of cartography as their forebears had seen, saw that vast map was useless, and not without some pitilessness was it that they delivered it up to the inclemencies of sun and winters. It's a bit of a clumsy language, probably has to do with the time. In the deserts of the West, still today, there are tattered ruins of the map inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. So that's Borges on the exactitude in science. And here is Genesis 11.6 from King James Version. Come, let us go down, and there confuse their language, that they may not understand one another's speech. You get the point, okay? So modeling hierarchy then, all models are wrong, but some are useful. George Box, I think, was a statistician who said that, and he's basically right? Lots of models, people build models, many models exist, but they are all wrong. It's a bit harsh, but essentially they are not exact, but some are useful, so they can be used for making policies or taking decisions. So we can define the climate model hierarchy as the set of all configurations of models of Earth's climate together with some hierarchical structure in which model configurations are ordered from least to most realistic. This has been discussed by many people before as well in terms of various axes of complexity, details, and so on and so forth. In attempting to formalize this, however, one quickly realizes that a strict ordering of all configurations is not possible. How, for instance, can one compare a moist, non-rotating, cloud-resolving simulation in a planar geometry to a dry, rotating, coarse-resolution global simulation? One is not clearly more realistic than the other, at least in any general sense. The term hierarchy is thus a misnomer, and it becomes clear that if a strict hierarchical ordering is sought, it must exist along multiple axes simultaneously. This leads to a formalization of the climate model hierarchy as a Cartesian product space of individually hierarchical axes, which each representing a single model component. And this is how they think about it. So you have fluid can be compressible like the atmosphere, hydrostatic, so you make vertical motion assumptions, quasi-geostrophic, which has other implicit and explicit assumptions, and static as opposed to full equation with time terms. And you have rotational effect, which can be full Coriolis, can be a beta plane, can be an F plane, or you can completely ignore rotation depending on the scale you are looking at. And then that combines with ocean, which can be dynamical, can be just a column, can be slab, like a top layer only, or the upper surface itself, non-uniform surface temperatures or uniform surface temperatures. You can imagine many ways of doing this. And the land surface can be land plus ice, can be real land or idealized land or aquaplanet, as we saw in Dargan's model where land is all underwater. And then convection can be explicit and moist, super parameterized, you can go and see what these mean, or parameterized, and large scale and dry. So those are kind of the options. So you can see how many combinations can emerge. And then for radiation you have a spectral, gray, Newtonian, and fixed. Here you're basically taking a temperature difference with a constant, and so on. So spectral means you have all visible, infrared, and so on. So obviously there are many details, but you get the idea. So if you want to do further idealization, the 6 axes in this equation may be naturally grouped pairwise, so you can take it as fluid and rotation as a dynamics idealization or choice, ocean versus surface as a boundary forcing, so the atmosphere sees something, and convection and radiation, so you have bulk forcing. It's just a way of thinking. So here is a more complicated axis that I mentioned before. So you have dynamics and boundary, and then you have observations on this end here, and you are going from single column radiative convective equilibrium model. If you don't know what that is, you can look up in my climate modeling course. And you have bulk models here, and you have planar GCM with radiative convective equilibrium, or cloud resolving models as well. You can have Coriolis assumed to be 0 and make it more complicated. So in terms of Isaac Hell's terminology, you have elegant mid-latitude hierarchy. So cloud can be idealized, so you can have non-uniform surface temperature, uniform surface temperature, and then you have elegant tropical hierarchy versus mid-latitude hierarchy. And then you have a range of models here for the boundary and the dynamics. So surface, so AOGCM, atmosphere ocean, slab ocean with real land, slab ocean with idealized land, atmospheric model in comparison where only the atmosphere is running with the ocean boundary conditions prescribed, aquaplanet and slab where the planet has no land, aquaplanet with fixed surface temperatures, SPCAM, near global cloud resolving models, and here you have various other levels. Does it help us? Well, it just tells you that if you try to put a hierarchy framework on all the models, then you end up with a fairly messy phase space of all these things. So I won't read the caption here, but they talk about using the hierarchy. And what is the simplification? If you have a problem that you do not know how to solve, then there exists a simpler problem that you do not know how to solve, and your first job is to find that simpler problem and solve it, and then move to the other problem. That's George Polya. You can find out who that is. Jumping to section 3.3, you have to choose between robustness to model physics, so that when you have this, there are many people like Lorenzo Polvani who have give us ideas on how to test the models, all the models across some specific problem. So you get into many details if you chase this down down the rabbit hole. Hence, our truth is at the intersection of independent lives, said Richard Levine's. Well, whatever is the context for that. Let's read the modeler's conundrum. I'm being very brief, but we will just read a few things to get a sense that modelers worry about model hierarchies, even though hierarchy itself is not very well defined, and this framework is provided, but it's complicated. But as Isaac was saying, many people can develop their own models for various purposes, and they may publish something that is gone through peer review, make some advances in some process understanding or interpretation of the data in a particular context. But then how do you combine those? Or if somebody did something, let's say one data set in one location, and it looks very good in terms of the end-to-end analysis hypothesis testing, but then how do you know it's globally valid, or that it's a generalized theoretical finding, right? So what is the modeler's conundrum then? The previous section outlined some scientific uses and attendant risks of climate model hierarchy that I skipped, but the model hierarchy can also be put to use in the service of model development, which is what Isaac also said when he said elegant models have to meet the elaboration models and help them improve their elaboration model. For instance, single column models can isolate the behavior of GCM parameterizations without interference from large scale feedbacks. In another direction, higher resolution models such as large eddy simulations and cloud resolving models can be used to more explicitly simulate those processes which are only parameterized in GCMs. So general circulation models are coarse resolution global models, and they parameterize many things in clouds, in convection, and so on. But CRMs try to do cloud resolution. Large eddies try to do other dynamic processes, fluid mechanic problems, eddies, mixing, etc. in a more explicit way. Such process modeling yields insights which may improve parameterizations and can also be used to benchmark them. A good example of all these approaches is given by Siegel's campaign to study low cloud feedback. You can go find out what that is. This campaign performed intercomparisons of both single column models and large eddy simulations, and also found mechanistic insight through a detailed LES study. So again, the trick is, will those mechanistic insights help improve the large scale or GCMs, which let's say are being used to provide information to policymakers and decision makers. Such efforts, however, do not always lead to the hoped for improvements in parameterizations and hence GCM performance. The central difficulties are similar to those faced by Borges cartographers and the denizens of Babel. In constructing models and parameterizations especially, we can only crudely represent reality. Yet at the same time, we are constantly changing these representations and making them more ornate, so old ones become obsolete and their replacements ever more unwieldy and harder to understand. Furthermore, we are focused not on one map of the empire, but many whose subtle differences make it hard to translate knowledge of one into knowledge of another. Okay, if you understand clouds, does that improve your knowledge of rainfall? If you understand rainfall from one approach, do you then improve clouds? How are they related? You can use many examples. So here is an example. This is the model's conundrum. So you are looking here at latitudinal scale, let's say going, it's a limited domain model going from minus 5,000 kilometers to 5,000 kilometers, let's say along zero longitude, and you have time in days and these are different models. So you have here models conundrum as Hofmüller diagrams of precipitation in energy units watts per meter squared from GFDL's AM 2.1 model. Simulations performed in a two-dimensional mock Walker cell configuration, so that's a zonal circulation, with non-uniform surface temperatures prescribed as a longitudinal distribution. A striking diversity of precipitation patterns is produced by varying only the column physics as follows. AM2 default including a minimum horizontal momentum performed minimum momentum entrainment rate for convective plumes. So if you don't know, don't worry about it. A critical cloud work function, so that's from for plume activation. So these are particular convective parameterizations and how convective momentum and dilute plume approximation, etc. happen. Vertical transport of horizontal momentum performed diffusively with a contribution to the diffusivity from convective mass flux. This is B is AM2 default except no minimum entrainment rate, and basically you are taking the same model and you are changing various things, and you can see how different the rainfall looks. Okay, that's just to give you a lesson. So how long am I in this podcast? 15 minutes, and I just have a few more slides, but they have a lot of text. So let's come back and read about elegance then and now with a cute quote from Einstein, and I'm gonna do that after lunch if I get time today, but otherwise I will follow up on another day. I have to do just squeeze in the time to do these podcasts because I can't always set aside time to do one whole set of podcasts either. So either way, you will not see any discontinuity. Okay, see you in the next podcast.